49th Terzaghi lecture tonight. I'm very honored to introduce our Terzaghi lecturer, Skip Hendron, somebody I feel like I've known a long time. I heard lots of stories about Skip when I was in graduate school. Born on 4th of October 1937 and entered the University of Illinois at Urbana-Champaign for his bachelor's degree, earning that in 1959, his master's degree in civil engineering in 1960, and his Ph.D. in 1963. He joined the faculty in civil engineering at Urbana, actually as a research associate in 1961. Did a short stint in the military service at the Corps of Engineers, the Waterways Experiment Station from 1963 to 1965, and climbed through the ranks of the professorial ranks through the 60s, reaching the rank of professor in 1970. Skip retired in 1994, retired from university service, but still remained very active as a consultant, working on projects all around the world. Still continues to do so today. During his time at the university and after, he worked very closely with Ralph Peck, another legend in our profession, and really had an esteemed career working on a variety of different interesting topics, working on nuclear power plant foundations. The list of nuclear power plants that Skip worked on is really remarkable. Working on static and dynamic stability of rock slopes for the Alaska pipeline, a pioneer in rock tunneling and underground openings, and an expert in the assessment of large dams, something we'll hear about today. And in 1983, Skip was inducted into the National Academy of Engineering. So with that introduction, I'd like to invite you to come up, Skip, and present your Terzaghi lecture.
Okay, thank you very much. Just a few comments first. I guess other people in different age categories mentioned when they may or may not have come in contact with Dr. Terzaghi. I never really had discussions with him, but when I was 19 and took my first soil mechanics course at Illinois under Tom Thornburn, or the Peck, Hansen, and Thornburn, and during that semester, we were divided up in groups of 3 persons, and we had to run a group consolidation test, and different people were designated to come back at different hours of the night to take the dial readings. Okay, I was elected on one of these nights to come back at 10 o'clock. It happened to be the day that I saw Terzaghi for the first time, and I attended a lecture that he gave. It was the very first time for me at 19 to hear him give a lecture on case histories. It was very obvious he never did give a lecture at Illinois on the details of the technical topics. It was damn clear that he thought everybody should be aware of the details of the technical topics. So he was offering his judgment on case histories of the job that he was working on. Well, that night after the lecture, I went into the laboratory, Roy Olson's laboratory, to read the dial gauge of the consolidation test, the first consolidation test I was ever part of. And when I went there, I noticed somebody had fooled with the paper and had marked down the dial reading. Okay, I asked Dr. Thornburn the next day, who in the world was messing with our consolidation test? He looked at it. He said, well, the initials there are KT. He said, he said, so Terzaghi had read the dial reading, and I thought somebody was in there messing around with our consolidation test. And so that was my first indirect contact, but I didn't ever really discuss things with him. That was like in the fall of '57 when I was 19. When I became a first semester graduate student, that would have been the fall of 1959, Yves Lacroix, who some of you may know, was working on his Ph.D. thesis for Terzaghi on Mission Dam. When it come time for Christmas vacation of that fall semester, Lacroix said to me, he said, Terzaghi wants some tests run on the friction angle between the rock flour up in the dam site there and a geomembrane that he's thinking about using in conjunction with the silt for the core of Mission Dam. Lacroix asked me if I had time, and I said, sure, I make time available for that anytime. And he said, how much you're going to charge me per hour as a civil engineer? Okay, this is the first big decision I had to make. What was I worth per hour as a civil engineer? I was top in my class as an undergraduate and was just beginning my graduate study. My father was a contractor. This is one of the reasons why I run into soil mechanics in the first place. From the time I was first grade, I saw just about every basement and the glacial soils from the time I was in first grade. I was interested in that stuff just to see what was turning up in the basement excavations. But anyway, my dad was a contractor, and I knew that the highest paid guys he had on his company were the bricklayers. And I knew that because I mixed mud for them. And I knew how fussy they were. Okay, they made $3.50 an hour. And so I told Lacroix, well, I ought to be worth as much as my dad's bricklayers by now. Okay, so he said, that's okay, I'll go run this past Dr. Peck. The next day he come back and he said, well, Dr. Peck said it's okay. But he said, don't tell the rest of the graduate students because they're not making that much. Okay. So that was my closest contact with Dr. Terzaghi, but I never really discussed anything with him. But I did hear every lecture he made at Illinois before his health made it so he couldn't come back there anymore. But it was worthwhile listening to his lectures. We had a lot of people outside the university come over. Jerry Leonard's usually brought a group over from Purdue to listen to those lectures, and it was an interesting time. I didn't digest all that at all at 19, but I did like soil mechanics, and I wanted to specialize in that area after that particular semester with Dr. Thornburg. He's the first full professor I had as an undergraduate, and that meant a lot. Being taught in a class of 15 people only as a first semester junior in undergraduate school is a good thing. Okay, in my lecture, I'm also going to talk about some case histories. The case histories today will be those case histories, not necessarily the biggest project I've ever worked on. That's not the objective. I want to cover some case histories where everything that happened resulted in full breach of the reservoir. It happens on small jobs actually more than it happens on the big jobs, but it happens, and it shouldn't happen. Okay, so I want to look at some of the lessons we might learn from that and talk about these particular case histories because there are certain details that were done, and they illustrate if you once have one conception with respect to a project that's wrongly conceived, it affects everything thereafter, and it's hard to get it turned around. In the technical design aspects of any dam project, and this doesn't necessarily mean the embankment itself, it means all aspects of the hydroelectric project. You got to be concerned with spillway problems, you got to be concerned with the embankment. You should be guided on all these. You should consider the modes of failure. Try to find out all of them. You should be guided by precedent of what's happened on other projects. You should be guided by past failures where you've had uncontrolled breaches. You also be guided by case histories where you've had undesirable behavior, but it didn't really breach, and somebody through field observations have caught the mistakes, and you had a chance to remediate it before it failed. And you can also take advantage of case histories where you've had acceptable performance compared to the type of structure you're trying to make decisions on at this time. You call upon, in addition to precedent, the theory of seepage, statics, dynamics, material properties, and the thing that used to be forgotten a lot is the geology of the foundations, both in terms of deformation characteristics and seepage characteristics. Let's go back from case histories and see what we have for the most frequent causes of failure of dams. One of them obviously is overtopping. Another one is a mode of failure that Terzaghi talked about, but a lot of people still don't understand how sensitive it can be. It's piping by backward erosion. Less frequent causes, but nevertheless some causes, are static stability, liquefaction of foundations, and liquefaction of hydraulic fills. For concrete dams, for the most part, it's a possible sliding on the foundation, whether it be an arch or a gravity dam. Examples of failures, if we just categorize those, some of these here are a little bit older, but most of these failures have happened since I've been an undergraduate, graduating undergraduate school in 1959. Sheffield Dam is a liquefaction failure out by Santa Barbara in 1925. Baldwin Hills Dam occurred in 1963. Concentrated movement along the fault caused by oil subsidence and oil extraction. I think I'm going to have to do a Marco Rubio. Okay. Teton Dam, piping on first filling. There was really an omission of a filter in a right abutment between a pipeable silt and open joints in the rock. So quite often piping failures doesn't involve all the little intricacies of the filter criteria. It's because somebody totally left out the filter. That's really what happens. After Teton in 1976, 79, the Martin County Reservoir failure, piping in the first filling, and I'm going to talk about that. The Gohu Dam in China, it's a concrete face rock-filled dam, failed in 1993, and that was a typical concrete face rock-filled dam with steep slopes, one on 1.4, both upstream and downstream. And instead of having rock fill, it was supposed to be a gravel, which can be better than rock fill because the gravel is stiffer. But for stability reasons, it had about 30% sand. And there was a level where the water level got up to the joint between a parapet wall and a concrete face slab, and it leaked. And that water was enough to make the 1 on 1.4 slopes unstable, and it failed on first filling. So once you go to those steep slopes associated with concrete face rock-filled dams, you got to keep the water out of it, especially if it's dirty. Silver Lake Reservoir breach, 2003. I'm going to talk about this one. This is where a fuse plug foundation with fuse plug was used to establish a new spillway to handle PMF that the project previously had not been subjected to in design. It was to improve the design of the Silver Lake Reservoir and the dikes around it. The next failure is Taum Sauk Upper Reservoir breach in December 2005. This was an overtopping failure of a project that had been constructed, finished constructed in 1962, put into operation in 1963. For concrete dams in 1928 in this country, in the Los Angeles area, St. Francis Curved Gravity Dam failed, sliding on the foundation. The most significant failure during the time since I graduated, to the 1959 M.ASCE arch dam failure in France, sliding on the foundation. On both of these jobs, there was no grout curtain and there's no drainage curtain to control uplift forces. It's amazing. Terzaghi come up with the principle of effective stress clear back in the early 20s. And the concrete dam design people really were behind the times of soil mechanics. It's amazing how many dams were built without the combined grout curtain and the drainage curtain to positively control the uplift pressures. Example of static behavior requiring remediation, 1975 Wolf Creek Dam. Corps of Engineers increased seepage and required construction of a cutoff wall, and there's a subsequent revision of that. Tarbella Dam in Pakistan on the Indus River. That had no cutoff, a dam higher than 450 feet, and there was a blanket went upstream for 1.7 kilometers, and relief wells on the downstream side to relieve the pressures, but nevertheless there was a very pervious gravel seam. And They were actually fortunate because tunnel number 2, the gate for tunnel number 2, a power tunnel to a powerhouse, failed. And the failure of that gate, all the water in the reservoir emptied through tunnel number 2 and exposed hundreds of sinkholes in the upstream blanket. It was a bad thing for tunnel number 2, but it turned out to be a fortunate thing that was corrected for the behavior of Tarbella Dam. 1977, coal-brine arch dam in Austria sheared about an inch through everything in the foundation and the base of the dam. It required a big buttress at the downstream of this arch. The arch was very thin. It was at a particular time when the structural engineers were getting thinner and thinner and thinner, like the structural engineers did previously in this country for Tacoma Narrows Bridge. I might say that it's nice to say I would have put a drainage curtain in M.ASCE. M.ASCE was so damn thin there wasn't room for a drainage gallery, actually, if you look at the dimensions of the base of the dam. Morris Shepherd Dam on the Brazos River in Texas, 1987. There was evidence that, and this is an Amberson Dam, which is a very light dam. Structural engineers out of New York City had a patent on this type of dam, but it is very light. There were multiple buttresses on a 40-foot spacing. There was a group of those buttresses moved about 5 inches, and after you looked at the uplift forces, which were big, that had to get multiple drainage and filling in weight between the buttresses, so we ended up with a weight there was darn close to what a gravity dam should have been from the start. It was on a shale foundation. You ordinarily you make the bad decision in step number 1 by putting that type of dam on a shale foundation. They're not compatible. Importance of significant details in dam inspections. There's people who do dam inspections, and there are people that do dam inspections but don't really find out very much. Not necessarily very perceptive and not necessarily very detailed. Most significant observations, you want to have good measurements of both horizontal movements and vertical movements. The water flows, recent changes, whether it's clear or dirty. Concrete structures, you want to look at the cracking pattern. Development of sinkholes, obviously. Evidence of pipe materials, piezometric measurements, piezometric levels. There are recent changes in the piezometric levels. Displacement measurements, consider settlements, XY surveys, pendulum measurements on concrete dams, extensometers, to really get accurate movements of different areas of something like an arch dam foundation. Inclinometers and crack opening measurements. Evaluation of displacement measurements. You want to know if the displacements are continuous along the structure or whether there are offsets indicating offsets in sliding movement between various regions of the dam. You want to know if the displacements stabilize with time at constant heads or they're increasing as the heads stay constant. The offsets in the displacement pattern or increases in rates of displacement at constant reservoir levels are concerned. You must investigate if the movements of concern can be measured within the accuracy of the surveys. A lot of times when people are talking about displacements and you really investigate the accuracies, the plus or minuses on the accuracies are in the same order of magnitude of what they contend the displacements are. Evaluation of observed cracks, you must establish if they're old or new. The crack openings open. It's a function of time. These geometrical relationships, the orientations of the crack with respect to the structure may indicate certain important characteristics of the dam behavior. Sometimes cracks really are harmless. In other orientations, they're an indication of potential relative movement or sliding of the dam. Evaluation of water flows. Gradual increase with time may represent gradual deterioration of one element of the structure. It may not be a safety problem. Abrupt increase in flows are nearly always a cause for concern. Abrupt increases of flow or dirty water is usually a great concern. Gradual decrease in flows of drains into concrete dams accompanied by increase in piezometric levels may indicate clogging of the drains. That's easy to rectify by some combination of cleaning the drains or drilling more drain holes. For that, you have to provide for proper sized drainage galleries and so forth so forth in the design from day one. Otherwise, you can't do those kind of things. In most concrete dams, once you build the concrete dam, additional drainage is about the only thing left in your war chest to do. So you better darn well provide for it. The first job I would like to talk about, it was the piping failure at the Martin County, Florida Power and Light location in October 1979. Lake Okeechobee, Atlantic Ocean. This is a location of the Martin County cooling pond for Florida Power and Light. At that time, there was an 800 megawatt station that cooling water was used for. Today, at that site, there's 4,500 megawatts, all burning natural gas at this point in time. Okay, if we look inside the red square, this is the geometry of the reservoir. This is the power plant location right up here. And you notice we got, and it'll show in a better slide later, but there's a canal running along here. And you see, except for this thing, which is the Barley Barber Swamp, you see that this pretty much runs, this west wall of the dike runs parallel to the canal. It runs parallel to a railroad. And down in here, you see there's a deviation. And what happened here when this structure was being built in the 1978, 77, 78 time, there were some borrow pits between the railroad and the embankment. Okay, so they made a detour away from the borrow pits. And let's look at the next slide. This shows a little bit better view. This is a canal called the L65 Canal. There's a railroad running parallel to it, but between the canal and the embankment. And at the time this was built, there were borrow pits in here that they used the dirt to build the railroad embankment with. And that was very important. It was a deep borrow pit. And the engineer calling the shots on this basically changed the alignment of the dike such that if you considered seepage entering the upstream side of the embankment, and that seepage path going over to the borrow pit, which was deep enough to take flow through the sands, that the average gradient would be 1 divided by 20, or 5%. Okay, he had made the decision at that particular time that he was smart enough to come up with the critical gradient. Now, it pays then to be a dumb farm boy like me, where I don't think I'm clever enough to come up necessarily with that magic number. If you don't come up with that magic number, what do? You either fill in the borrow pit or you put a filter on it. It's best not to have to be smart. Sometimes the guys that get in trouble on these more practical jobs are the guys with the Ph.D., okay? So sometimes I leave that off in front of my name, okay? Besides that, when I was at Illinois and Professor Deere had sort of talked me into going on for a Ph.D., I called my contractor father one night on our phone and told him that, well, I decided to go on for a Ph.D. There was silence on the other end of the telephone. And he said, what the hell do you want to do that for? Okay. So the L65 Canal, if this is Lake Okeechobee, looking at it in detail, the L65 Canal along the west side of our embankment has a gate structure here. Now, on the L65 Canal side, normally that water level at that time was plus 19 above sea level. Today, I did an inspection on that embankment in November 2012. It still is 19.1 feet above sea level today. But there's a gate structure there, and if you raise that gate, the water level in the canal will fall to the level of the St. Lucie Canal that goes all the way from Lake Okeechobee out to the Atlantic Ocean and goes in the ocean around Stewart, Florida, between there and St. Lucie, Florida. So if you would open that gate, the water level in the L65 canal would fall from 19 to plus 14. As you'll see later on in this little discussion, at that particular time, there was some kind of a range war out there between the sugarcane growers and the grapefruit orange growers, and each one wanted a different level in that canal for their own selfish interests. I never did understand fully what the problem really was, but on a Saturday, some guy went out there with his gun, shot the padlock off that gate, which was October 27th, and 3 days later, the dam failed after being there 18 months with only a 5-foot level change in the L65 canal. Okay, that's why I showed this picture. Okay, along the St. Lucie Canal in a different location, St. Lucie Canal is still around plus 14. This is the reservoir we're talking about, the Martin County Cooling Reservoir, at 37 at the time that those things were happening, plus 37. And this is where water was taken from the St. Lucie Canal through a pumping structure here to add water to the cooling pond if they thought they needed more water. This is a spillway to reverse the flow if they thought they needed to get rid of water in the reservoir as a spillway. Now, if we expand the area shown in this critical area, this is a recent photo from Google, which their operation didn't exist at the time that the railroad bar pits were there. And this is what diagram looked like about the time of the failure. This is the location of the breach. This is the railroad. And this gives us the limits of the L65 canal. And what happened is the average standoff distance between the upside of the embankment and the first part of the borrow pit, the nearest part of the borrow pit, was about 340 feet. The head difference multiplied by about 20 is how they got to 340 feet, given an average gradient of 1 divided by 20. The way it happened, it was a little bit higher than that at the north end of the borrow pits where it failed because somebody didn't turn it over quick enough, and it was like 290 feet. Okay, it failed where it was 290 feet. The embankment, all the way around, was the type of embankment when I first started teaching some undergraduate classes at Illinois in 1961. We built embankments like that in the laboratory to show the students if you didn't have a drain that they would fail. Okay? Okay, we had a soft cement facing, which really isn't necessarily impervious relative to a fine sand, about the same. But it does give you a riprap protection. Okay, in the earth dam classes, after Dr. Peck retired and I taught that class for 20 years, told my students in the first lecture that, and Scott Olson here can probably repeat it, there are certain elements to the dam that you want to have. You want to have the riprap that they have here. You want to have a drain. You want to have a filter. You want to have stable shells, and you want to have a cutoff. Okay, you can probably get by with an omission of 1 or 2 of those, but you sure as hell can't do without 3 of them. Okay, this one didn't have a drain, didn't have a filter, and didn't have a cutoff. So the seepage was uncontrolled. It sat there for 18 months before it failed, under the normal conditions of the L65 canal. It got to be so wet at the bottom, there was seepage coming out on the downstream surface. The roadway here got to be so wet that they couldn't run a pickup truck at the toe anymore. The inspections were being done going about 5 miles an hour on the Crest Road. It was performing that bad, but it certainly wasn't failing. Okay, Florida Power and Light had 3 of these reservoirs built about the same time by the same design construct unit. One here near the Palm Beach area at Martin County, the SANFORD plant north of Orlando, and the MANATEE plant over by Tampa. They all 3 were wet, but the Martin County one, which failed, was the only one built next to a borrow pit that was deep enough you could get possible piping from the upstream side of the embankment to the borrow pit. Okay, if you look at the plan view of the breach, this is where the embankment turned. The flow came here out of the reservoir. Over here, here are the borrow pits. I think it's obvious from this figure that the distance from the end of the borrow pits to the upstream side of the embankment was shorter here than it was over here where they made the full turn. So in their surveying or whatever, the turn was probably made too late. It should have turned farther away to the left to get on the new alignment. This is another aerial view, and it's obvious from here. This is the upstream part of the one of the borrow pits. And the 340 feet here was from the borrow pit over to the upstream side of the embankment. And that's what gives an average gradient of purposely of 0.05 or 1 divided by 20. Just another view looking south, and you can see the same elements. And this is the borrow pit again. Water went like this and out. The other thing is that you'll see, or we did see, there was enough drawdown around this breach area that there was a rapid drawdown of the soil cement part of the design for close to 1,000 feet on each side of the breach. This just is a view from the reservoir looking where the water went going straight west. This is looking north along the intact part of the alignment north of the breach. And this just shows the pile of riprap that was left. If we look at some of the key facts, the cooling pond is about 91,000 feet long, or about 17.2 miles. The embankment dike with the soil cement interior facing. We had a crest elevation of 50 feet on the embankment. The interior soil cement slope was 1 vertical to 2 horizontal. The exterior slope was 1 to 3, which is usually necessary to be that flat for mowing, as for nothing else. The pond was filled to elevation 37 in 1978. About 18 months after filling, the dike failed at 11:30 p.m. on October 30th of 1979. The failure occurred on the west side of the pond at station 422, where the dike was adjacent to the pre-existing borrow pit for construction of a railroad embankment. The ground surface at the base of the dike was about elevation 22, and the water in the borrow pit was at elevation 19. The depth of the borrow pit extended down to elevation 0. So that thing was a significant depth to it left open. A number of sand layers that could have piped into the open borrow pit. And the other thing about that type of situation, it's uninspectable. Even if you walk along there, you can't tell where the sands are. This is something you just don't want to develop in your designs. Have a design of water behind sand embankments on sand foundations. You have to take a lot of precautions to make sure that you're really inspecting it, which means everything for a significant distance has to be dry and it has to be mowed. You don't really have a choice. The L65 drainage canal on the west side of the railroad had a water elevation of plus 19 and a depth of about 15 feet. The L65 canal and the borrow pit were connected hydraulically by culverts under the railroad embankment. So if the L65 canal changed one way or the other, the borrow pit would go hydraulically with some lag time with the L65 canal. About 3 days before the breach, the L65 canal fell to plus 14 due to someone shooting the padlock off of the gate structure we talked about. The close chronology of the failure time with the time of the incident strongly suggests that the changes in hydraulic gradient caused by these changes in levels of the L65 canal triggered or precipitated this failure through piping through the foundation of the dam to the borrow pit. In November, by now, November 11th, not very far along, 1979, there was a special board of consultants appointed by Florida Power and Light. I was one of these members, as was John Smertman from the University of Florida then. And John is still active now. Paul Shea from the Jacksonville District of the Corps of Engineers. And Bill Swiger was chairman of our group, a very wise engineer from Stone Webster, Boston, long before they were bought out by Shaw recently. We submitted a report by July 16th of 1980. And it was almost rebuilt by about that same time, over a very short period of time. Bill Swiger was like a geotechnical father to me in this business. He had a hell of a lot of wisdom and did it in a very nice way. And I consider him as one of my teachers, even though I never had him for a lecture in a university class. There's different ways of teaching, and he had a lot of wisdom to teach. Okay, if we just looked at a flow net in a horizontal plane, you get some idea on the concentration of the flow lines and the concentration of gradients due to the geometry of the embankment and the geometry of the borrow pits. So it's not just the average that counts, but there is almost like a stress concentration factor. As part of our investigations, we had trenches done to define the geology and the stratigraphy of the sands. And some of the most important things, if you look at the C unit, there's a white cohesionless sand, and if you're going to develop piping, you have to have a mobile cohesionless layer, but you also have to have a roof over the top of it, which will permit the pipe to form without collapsing. That roof for the white sand would be this hardpan layer right here. Okay, down in the D units, there's a light brown sand here, which is very cohesionless. And right above that is this layer here, a sand with some clay in it that can provide a roof for piping in the D unit. So we have two layers there that have the potential to pipe that are mobile, they're cohesionless, no clay in them, that have roofs over the top of them to permit a pipe to form. I've shown the same column there, and it's important to look at the percentage passing the 200. If you look at the white cohesionless sand, there's nothing passing the 200, and there's no clay. If you look in the light brown sand in the bottom of the D unit, it also has 2 to 3% passing the 200. It must be silts because there's nothing in the limits or anything that suggests that you have a clay. So it's also mobile, potentially mobile. Okay, during the construction of these trenches, this happens to be the upper white sand in the C unit. This is a hard pan. When they made the trenches, just to define what the units were, the white sand started running out, just from inducing a gradient from the regular groundwater table there when you make the trench. It showed right in front of you that it was piping, and the hard pan showed that it was a capable roof. This isn't rocket science. It's just sort of paying attention to what you see when you open up a cut. And we had a geologist doing this, and so it's the importance of the geology in the things that we do to supplement or do in addition to the soil mechanics details. This, I know you can't read it, but I've shown this only to show where the vertical and the horizontal scale is the same, the geometry of the flow to the borrow pit. The borrow pit was down around 0. The ground elevation was 20. So it was close to 20 feet deep. And if we look at the next one, this is the same profile magnified so you can see. This shows the geometry of where the white sand was for the upper pipeable unit. And this shows the D unit, which was the brown sand, which was also pipeable. And in the relationship to the borrow pit, the white sand comes comes in up here below water where you couldn't see it. It would be uninspectable. And the brown sand comes in towards the bottom, but nevertheless it can still exit in the borrow pit because it's down around zero for the bottom of the borrow pit. The geometry is there, the two sand layers are there, and the chronology of the 3-day behavior sort of speaks for itself. A lot of times you've got to be more leery about the tailwater decreasing can be more effective in causing these kind of things than the upstream increasing. It's because it starts the piping procedure from the tailwater. And it's one thing, if you got piezometers on a dam, on the downstream side, if somehow they start decreasing, that's not necessarily always good. It means that you may have a pipe forming that drains it and is a cause for the piezometer going down. It can also give you that sort of behavior, like one dam I worked on in Argentina, which is sandstones with joints full of gypsum. Okay, with time, from the downstream side, sometimes the gypsum starts dissolving, and you've got piezometers decreasing there, and it's not good. It looks good for stability, but it means the gypsum seams are being dissolved. This is just a picture of the cross-section in the failure area. The other thing that's interesting here is that depth of that hole was dug from the original ground surface of around 22 to minus 10, showed a 32-foot deep hole. So when you're looking at the effects of these things, even though the heads are small, when the stratigraphy is sand, that excavation depth that can occur in these problems can give you effects that can be very bad. There was a cooling pond for a nuclear reactor with a cooling pond like this for the operation cooling, even though there was a class 1 cooling in a different spot. But that whole situation was reassessed for that case in case a hole like this was dug because of the proximity of that particular dike to the containment building. A cartoon of what happened here. These aren't to scale. These are just my sketches showing the L65 canal plus 19 for most of the 18 months, the culvert on the rear embankment, the borrow pit at plus 19, the ground surface at plus 22, the distance between the upstream side of the dike and the nearest point of the borrow pits range from 290 to 340 feet, and the reservoir is 37. If you look at the calculated gradients, as I mentioned before, you get about 1 on 20 for the 340 feet, and you get about 6% for the 290-foot distance. All really, for practical purposes, they're about the same, except on the north end of the borrow pit, you got the concentration factor of the geometry that we saw acts like a stress concentration factor in a stress problem and gives you local gradients, which is what counts for piping, that are higher. And the water did what it was supposed to. It caused piping on the north end of the borrow pit. Okay, this just shows the change in heads and the changes in gradients and the fact that the failure occurred after 3 days and that the increase in gradients caused by the water level decreasing just 5 foot increased the calculated gradients by 28% from what they were for 18 months before that. So the special board concluded that the most likely failure was piping by backward erosion between the north end of the borrow pit and the upstream side of the dike. The piping could possibly have occurred in both the C or the D units we spoke of. Any possible remedial measures considered should be filling in the borrow pits, constructing a filtered toe drain around the entire dike. This area was, regulatory agency was South Florida Water Management District. They had a say-so in what we have to do to rebuild that, to salvage the 800 megawatts that was already installed there. So if you look at all these things, one of the things we considered and actually ended up doing, actually pumping the toe drains such that the hydraulic head and the header pipe is at the elevation of the header pipe, so it doesn't flow under pressure. And it's no longer a passive system, but is an active system for controlling the drain. Construct a partial cutoff around the inside of the dike for the entire length of the embankment. Yours truly wanted that, and between the two consulting boards, the original consulting board that sort of had the failure. Our new consulting board, which were new men on the block, we still had to meet, like the Republicans and the Democrats, to try and hammer out something, because everything good that we wanted to do, it automatically implies that it's a mistake the first board made. Eventually you have to do something. Okay, we did all of these. I was a minority of one on the last point about the partial cutoff wall until certain things were observed in exploration. Anyway, it's one of the things we did. By the way, Bill Swiger and I made presentations in front of the South Florida Water Management District people, which were elected. They were like politicians. They were elected. Okay. We both covered different topics and said what a good change in design this was, and it was going to cost about $80 million for these changes, where the original cost for building the whole embankment for 17 miles was only $45 million. When we got through with our little lectures, the elected guys that wanted to make points with all their voters in the audience said, well, he said, it's all well and good what you guys just told us, but about 2 years ago, the other board told us how good their design is. How come we should believe you? Well, we made another little lecture and finally convinced them, but it was a good point to make. Because once something like that happens, it doesn't do the profession any good. None of us. Here is a filtered drain system up to the 41 feet, where the design level of the water is about 37. And you'll see the outline of a pump here. Maybe not very well, but there's a sump with active pumping taking place significantly. So the water level varies, but just below the drain, so that the drain is never under a positive head. And this is just an outlet of the filtered drain at that elevation. This is what the design looked like in the area of the failure, since it's a little bit different. And it's a deeper starting point than the others because of the deep hole that was dug by the water. Today, this is what it looked like. It's what it looked like when I was inspecting this with Les Bromwell, an MIT graduate, in November 2012. It's mowable, it's dry, nothing is wet. Our entire phreatic surface is below the level, and any kind of equipment can run there at any time, and you see at a distance there one of the sumps. There are 29 of those sumps, over 17 miles at average. The spacing differs with the head. We got them a little bit closer where the head's higher, a little bit farther spaced where the head is lower, the topography is higher. But there are 29 of them, and it gives spacing of those sumps between 2,300 feet and 3,000 feet. There are many piezometer lines. This happens to be a piezometer line at station 422, right where the failure occurred. It's always of interest. This time, the L65 canal was at 19.1 feet, just like it was years and years ago. The reservoir elevation is 33 1/3 feet. They've never really been fully allowed to go back to 37 feet by the South Florida Water Management District, but they're still managing to cool 4,500 megawatts with the elevation at 33. So there's no point to go up there just to pick a fight, as long as you get the cooling you need. By the way, this may sound political, and if it is, well, I still say it, okay? At this site, we got 4,500 megawatts generated in this little 30-acre space where the power plant structures are, even though we got 6,000 acres for the cooling pond. To make brownie points, Florida Power and Light is building a solar field. Okay, the solar panel field is 200 acres. You know how many megawatts it generates? 75. 75 relative to the 4,500. The other thing that's not indicated by the environmentalists is if a hurricane comes there and breaks some of those pipes with the fluids flowing around through the solar panels, you really do have a pollution effect. Anyway, I'm not going to talk any more about that. But coming from the farming country of Central Illinois, where they're polluting the visual area with all these damn windmills, I'm prejudiced on that point. I don't know how some of these farmers can stand to live that close to these big windmills. They don't. This is a similar phreatic surface, station 440, just a few hundred feet down by the sump that I just showed there. The other thing is, this is a cartoon of what we're doing at Martin and what we've done at Martin since 1980. It went back in service there in 1980. This is not the scale, but this just shows what we're doing with the sump. And what happens now when the pumps pump it, the water just doesn't go out to a distance. It's really curved back, and we pump it over into the reservoir. That way we don't have to deal with the variations in the acidity of the water and get into a fight with the environmentalists that don't recognize that natural seepage in a warm climate with the vegetation like you have in Florida, it gives you natural acid type environment. This is why you get the sinkhole like happened in Florida a few days ago. It's not new information. So you know that this was a very expensive system, and usually you don't have to do positive pump down like we're doing here. There's a certain expense associated with that. But it's not great compared to the money people get on generating 4,500 megawatts. Now, at the other site, MANATEE, those sites were just as bad, just as wet. But they didn't fail because they weren't built right next to a borrow pit like it was in Martin County. So there we have filter drains supplemented by relief wells that come up into the filter drain and then goes over to a swale drain which goes longitudinally along the embankment to keep the swale drain dry and to keep everything here dry enough that it can be mowed and it be retained to be inspectable. It's worked, and that cost is about 1/15, not 15%, 1/15 of the $80 million we spent on the active drain for Martin. A lot cheaper. At SANFORD, we don't have the relief wells. The heads are a little bit lower. We have a filtered drain, and the same thing to control so that the seepage doesn't wet up the ditch to make it unmowable and make it uninspectable. This shows the piezometric readings at MANATEE. They're significantly below the topography. It's mowable and it's dry. At SANFORD, we got the same thing. Just filtered drains to control seepage, a lot cheaper than the active pump down. And it's been working since 1980 when these remedial measures were made on all three sites. So some of the things to learn, the main thing to learn on Martin is don't use a rule of thumb thinking you're smart enough to know the exact average hydraulic gradient that will prevent piping. Go ahead and either fill in the borrow pit or put a filter there. Don't fight the problem. It is best to make a positive decision even though you don't have to be as clever and you don't have to be as smart. The next case history I would like to treat here is the technical reasons for release of the Silver Lake Reservoir. In May of 2003, there was an independent review panel appointed by FERC to investigate the causes of the reservoir released. I was a member, Mike Duncan was a member, and Nelson Pinto, who you may or may not know, he's a hydraulics guy from Brazil. He probably knows more about all the spillways in the world, more than anybody that I know. And this was one that did involve a spillway, and as a member of the board, I insisted that the government take great pains to hire a foreigner to be on our board. He's a member of the U.S. National Academy of Engineering, as is Mike Duncan. Nelson Pinto, although he's a Brazilian, he got his education in hydraulics at the University of Iowa in the Big Ten, who had a real tough hydraulics guy there by the name of Hunter Rouse, and the students he put out were really put through the paces. And this guy, to supplement that good education, has more experience than anybody else I know. And he certainly knew more hydraulics than me and Mike Duncan, and he made significant contributions on this particular job. I've worked with him on a lot of foreign jobs involving big spillways, and you got to have somebody with that kind of judgment and that kind of experience, also a good theoretical background in which to interpret the experience. This job of Silver Lake was in the Upper Peninsula of Michigan, where I've shown the red square, near Marquette, Michigan, about 45 miles west of Marquette, Michigan. And it's on the Dead River. And at these two locations, there's two dams that are concrete dams they're abutted by embankment dams, Hoist Dam and McClure Dam. And there's also a tourist park dam down here owned by the city of Marquette that when Silver Lake failed, the wall of water coming down went over Hoist and McClure dams. It overtopped the soil embankment next to Tourist Dam, and it failed. It's having to be rebuilt. This is just the concrete dams, but these also have embankment sections next to them. A Hoist Dam, over on this side, there's an embankment section that come very close to overtopping during this failure. And here's an embankment section next to McClure concrete dam. One detail that I found when you have these older dams and you have abutting embankment dams and concrete dams, you should always have the embankment dam higher. You don't treat them democratically equal because they're not. And if it's going to overtop someplace, we want to make sure it overtops on the concrete section. It sounds like a minor detail, but when you look at different projects, that simple thing is not followed. Okay, if we look upstream at the Silver Lake case, this is what it looks like in plan view. It's very complicated topography. There's a lot of little drainage valleys go off of this that need dikes to retain the lake. And if you just look at one end, you'll see that in this area there's a main dam. It's only about 30 feet high and it's about 1,500 feet long. Right next to that, in rock, there's a low-level outlet structure to let water out for fish downstream, or to let water out at a higher intensity if you really want to lower the reservoir level for some kind of a safety reason. And right in that same area, there's an old concrete spillway, only 100 feet long, of 10 different bays, separated by piers. That's only, the OG is only about 6 feet higher than the ground around it. And that reservoir's been there for probably 70 years. There's a dike that we'll refer to as Dike 4, a little dike over here, the lowest dike of all of them. And there's a Dike 1 here, and a Dike 2, and a Dike 3. Dike 2 is very important because later, when this project was modified, that dike was replaced by a fuse plug spillway. Okay, this is Dike 2. This is location where there's going to be a fuse plug when the project is modified. Now, this thing, I told you, failed in 2003. The way that it turned out, it's being modified to supposedly accommodate the PMF. In 2002, was between a combined snow melt plus the rainfall, was actually a wetter year in 2002 than in 2003 when the project failed. And this is important because the water level you see behind Dike 2 before there were any improvements made was 1485.8, and later on I'll tell you the fuse plug that was put on this area was made to fail when the water elevation reached 1485.5. That water level would have caused the fuse plug to fail, but it was safely handled by the old system before the so-called quotation marks improvement was made. So this takes you back clear to the beginning of medicine 2,000 years ago, where one of the rules was supposed to be that whatever you did wasn't supposed to do harm. Okay, we got a good example of that here. It does show the similarities between the civil engineering profession and the medical profession and our abilities to make things worse with our fix if we're not careful. The only difference between us and the medicine people, they kill one person at a time. Sometimes, no, I don't mean that a joke. If anybody that's in this business and is interested in dam safety, especially managers of utilities, ought to be forced to go to the Vaillant slide where 2,000 people were killed by that incident. And you still see the things that happen today and around there where the people, even though that happened in the fall of 1963, people are still affected by it. Okay, that just shows the elements of the structure, even though this is after the fact. This is the old low-level outlet structure, a long, narrow gate to govern the amount of water that goes out a 36-inch diameter pipe. This is the old spillway. Each bay there between the piers is 10 feet, and so you got 9 feet opening. The spillway OG there is at 1586.25 feet elevation. And in the one bay, 4 bays from the left-hand side, there's an open notch left down there to 1482.5, so that if you take those wooden stop logs off, when the water starts rising, water can go through there and tend to lower the lake level before the water reaches the OG level of 1486.25. I hate to bother you with all those elevations, but they really are very critical, especially those relative to each other. The purpose of this project originally was to raise water level of a natural lake, provide flow regulation to the 4 hydroelectric power plants downstream at Hoist, McClure, Forestville, and Tourist Park, those last 2 are owned by the city of Marquette. Tourist Park Dam failed as part of this failure. It's the most downstream one next to Marquette. The most dollar-wise damage on this failure was caused by jamming all the cooling stuff at a 1,000 megawatts thermal plant right before the Dead River exited into Lake Superior. So there were a lot of financial considerations between different teams of lawyers after this failure. The main dam crest originally is 1490.7 elevation. The ungated spillway, 1486.25 at the OG. What you just saw was the open bay closed with stop logs right up to the same elevation of the OG of the spillway. The perimeter dikes 1, 2, 3, and 4 of the original project were slightly different elevations, and if the water was going to rise and one place overtopping could take place, would have been at dike 4, which is 1487.7. Now this is an interesting plot put together for the panel by Mike Hendron, and it shows the differences that you can see if you just plot the ups and downs of the reservoir to low points. Low points develop between the winter and about May when the snow starts melting. You see that the water level went down to very low elevations. Here it's 1467.5 if you average all those low points from 1957 to 1988. And you see one of the things you tabulate here from the points that it spilled, every time it went over 1486.25, the spillway worked, is that the spillway worked with this operation once every 4.3 years. The other thing, if you look at the storage of the reservoir at 1467.5 versus 1486, there's 22,000 acre-feet of storage. This is why this project didn't fail over the years, even though it looks like an old, crude project. They ran it up and down like a flood control dam should be exercised, keeping in mind that they were looking at this project. Now, what happened in 1988? What happened in 1988 is that the project was changed from Cliffs Electrical Company, which is a subsidiary of Cleveland Cliffs, which was the whole economy of the Upper Peninsula in iron mines. Now, this was transferred to UPCO, the Upper Peninsula Power Company. They bought it, and they started going through the procedures that have to be gone through with FERC and so forth to get a license. And one of the things that procedure has in it is that the state environmental people have a say-so in a lot of things, and usually it's for the, how should I say this, not the average sex life of the fish, but the optimum, okay? Okay, so what do they usually do? They raise the low level permitted. Okay, in this case, it was raised from 1467, roughly, to 1477, 10 feet. Okay, if you look at the storage going from 1477 to the spillway elevation, then you can get 12,000 acre-feet of storage, where previously, the way it was run, you get 22,000 acre-feet of storage. Okay, now, for the PMF, you'll find that the inflow of that PMF, this is the other thing, when it gets under FERC, then they have to design for the PMF, and before they couldn't say they were designed for the PMF. PMF inflow is like 30,000 cubic feet, 36,000 cubic feet per second. If you look at the duration of that, which is 13 to 15 hours, not to that, but the total duration going up and coming back down, the area under that PMF curve amounts to about 16,300 acre-feet. Now, previously, the way that it was run held up the PMF could be stored in the reservoir because it reached in the low point during the time of the year that you get the snow melt and the rainfall. That's how come it operated successfully the way that it was, the way the old-time engineers determined how the project should be run as a flood control equalizing thing. If you start trying to satisfy too many things about water skiers, the fish, by the way, that lake out there in the woods, 25 miles away from any place, the fishermen went out there to fish all the time during this time. It didn't necessarily need the adjustments made by the environmental people. But what was done by the environmental people restricted and reduced the storage capability there by 10,000 acre-feet. So PMF, the way that it was run previously, could be stored at the time it was most likely to occur by the way that they run the reservoir without changing the structures. Okay, now when this rule of thumb was, this method of operation was changed, then the spillway worked every 2 years, basically, twice as often as it did in all the years before that, where it averaged close to four spilling once every 4 years. Okay, just wanted you to keep that in mind. Now, there's something else that I want to put on here with respect to things we're going to discuss several slides away. This 1485.5 put in red, when they changed the project, economically they thought they're achieving a lot by designing a fuse plug to fail when the pilot channels were put at 1485.5. That means that the fuse plug was designed to trigger and activate and fail and make the water go downstream. Now, when the fuse plug is designed to activate at 1485.5 and the OG of the spillway is 1486.25, that means that the damn spillway is never going to be any use to anybody. It's not going to flow one drop of water before the fuse plug fails. I'm not making a joke about it. I mean, this is just real, and it's a bad initial decision that you can't necessarily recover from. Something else happened when they changed the design to include the fuse plug where dike number 2 was and had the pilot channel at 1485.5. As part of that design, they said the normal maximum operating level should be considered to be 1481.5. So if it tends to go above 1481.5, somebody has to try and open the low-level outlet to higher flows. Ordinarily for fish downstream, it's 20 cubic feet per second. It has a maximum of 280 cubic feet per second. And if it went above that, you'd have to turn the low-level outlet on. Okay, now between that restriction on the design of the modification and the environmental thing, you see that these guys are expected to maintain that reservoir within a 4.5-foot range between 1477 and 1481.5. Not very realistic, and not necessarily thinking the whole problem all the way through. Here's the PMF is indicated what has to be happening. They haven't got the volume there, but I told you the volume of that's about 16,200 or 300 acre feet. Crest elevation of the main docks were raised to 1491.5. Spillway crest remained constant at 1486.25. Dike 2 replaced by a fuse plug at 1486.5 at the top, which is higher than this. But the pilot channels with an invert of 1485.5 are what's to trigger or activate the fuse plug, which is lower than the spillway. Which meant that the spillway after that point was useless. The foundation of the fuse plug is at 1481. So the fuse plug, the height of that is basically only 5.5 feet to the top of the fuse plug from the base elevation. And the length of the fuse plug was 265 feet. Now when you employ a fuse plug, you're only supposed to release a wall of water equal to the height of the fuse plug above the foundation of the fuse plug. The fuse plug is not supposed to erode deeper, which is why common practice is not to employ a fuse plug unless the foundation of it is on concrete over rock or unless the foundation is on top of rock that's unerodable. It's a concept that should be used that way. It would be unprecedented to use the foundation of the fuse plug on soils. Okay, associated with the design change, the stop logs in the fourth bay of the spillway were to be set at 1482.5, down from the 1486.25 that I showed you in the picture. And the modifications were constructed in August, September, and October 2002. And this was to accommodate the inflows of the PMF condition, these design changes that I just described. Now, so these were completed in October 2002. What was the date, does everybody recall, that this failure occurred? May 14th of, less than 1 year after the quotation mark improvements were made. Was that a PMF that caused the failure? No, it really wasn't. It was a 4.5-inch rain on May 10th and 11th, combined with a little snow melt in between, say, May 7th and May 14th. So, and this wasn't as wet a year as when I showed you at the beginning of this presentation the water up against Dike 2, that was 1485.5, which was the top crest of the fuse plug. So the rainfall that occurred in 2002, in June of 2002, would have also caused the fuse plug to trigger. Why am I telling this to soil people? I'm one. When you work on these jobs, you've got to look at all these things. And if you say, well, I'm only going to look at the slope stability as a soils engineer, and you're part of a board of consultants, you really got to have discussions on all these topics with your colleagues in the other disciplines. Erosion that may occur in the base of a fuse plug is one of those areas in between hydraulics and geotechnical engineering. And don't be fooled that the hydraulics people can answer all these problems on the basis of more and more and more hydraulic model tests. Okay? You've got to be dealing with somebody that's seen erosion or hasn't seen erosion and correlate it with the soils or the rock involved on the base of something like a fuse plug. Okay, so this was kind of a sad case in which these elevations were set of the fuse plug, which excluded any positive performance of the spillway. It had been there for years. The fuse plug was built in the area of Dike 2. It was built in a flat area. It's also important that just 100 feet downstream of that fuse plug, the gradient is 1.8% slope, which would result in higher velocities calculated where it's horizontal, and you can have higher velocities there eroding the channel, which worked back up towards the fuse plug. This is the geometry of the fuse plug. The top was at 1486.5. The top of the clay, or I should say what's considered the impervious, was 1486, which is also below the spillway. Now in the pilot channels, which is where the erosion is supposed to start and trigger the fuse plug, the top of the pilot channel is 1485.5, which was significantly below the top of the existing spillway. The top of the impervious is actually 1485. So it could really start triggering anytime after the water level got to be above 1485 as compared to the OG of the spillway, which is 1486.25. This is what the fuse plug looked like after construction in October 2002. This is the lake side, or the incoming flows from the lake would be here at 1481, the base of the fuse plug, and this is the downstream side of the fuse plug. Keep in mind the location of those boulders there. That's to stop previous guys from going across the fuse plug on what used to be a road there to the next dike. And this is the pilot channel. There were two pilot channels that were supposed to initiate the activation of the fuse plug. And this is the details of the pilot channel. Okay, we go back to the original dike number 2, 1485.8. That's a higher elevation of that water in June of 2002 than what it would take to trigger the fuse plug after the improvements were made by October 2002. Okay, we come to the time to where after the activation of the fuse plug took place. On the wood stop logs in the fourth bay of the spillway, there was a high water mark shown on the felt paper of 1485.6. That shows how high the water level got to trigger the fuse plug. Now, there is a view of the concrete spillway from the reservoir. Picture taken from the low-level outlet area on the embankment at 8:30 p.m. on May 14th. During that time, the fuse plug had triggered and the lake level's going down. And this is how much it had gone down. You see the wet area there by the time this guy took the photo at 8:30 p.m. on May 14th. It had already fallen that far. So the lake had been breached at the fuse plug, and this just shows how much it had fallen very recently. This is the backtracking this is the last reading that was taken of the reservoir on May 7th. Now this is something that had to be changed too. The guys that monitored that lake from the power company only read the reservoir level once a week. If you're going to be responsible and in charge of a reservoir, it should be read every day, no matter how you do it. Even after you send guys out in the woods, and it's hard to get there. Now it's automatic. After these kind of things have been, it's read and transferred electronically. But nevertheless, in those days, which wasn't that long ago, in 2002, 2003, it was read once a week. So that was the final data point before the failure. This is what we know the water level reached from the markings on the felt paper in the the old spillway, and of course it fell as the reservoir was breached. Now, these are just some photos of before the failure at 8:30 p.m. where somebody could see what was happening in the area where the fuse plug used to be. You see the current is so fast that there's standing waves in it. And this is what it finally looked like after the lake was empty on May 16th of 2003. It had eroded from the top of the fuse plug, which is 1485.5, down to elevation 1455 at this point in time. And there wasn't much water left in Silver Lake. For all practical purposes, it was emptied. And it wasn't emptied by a big bad PMF. It was emptied by what happened after 4.5 inches of rain on May 10th and May 11th combined. this is on the right abutment of where the fuse plug used to be. Where these boulders are is where the left abutment of the fuse plug was. This is where the right abutment of the fuse plug was, and this is where the elevation of the erosion took place down to elevation 1455. If you look what happened downstream from that water, this is the hoist dam, and the embankment section of the hoist dam come darn close to being overtopped, and it was only saved because somebody had the wisdom at some point in time to make the earth embankment just a little bit higher than the concrete dam. This is the hoist dam at a different location. This is McClure Dam. McClure Dam at a slightly different location. And the other thing you see at McClure Dam, this is the embankment section, which was purposely built higher, and you can see it's not in danger of overtopping. And all the overtopping has taken place over the concrete spillway, plus a part of the non-overflow section of the concrete dam. Okay, the design velocities in the fuse plug channel for the PMF was determined in March 2002. They had calculated velocities in the water at hour 43 of about 9 feet per second. The maximum velocity was compared to Natural Resources Conservation Service guidelines that set the permissible velocity of our grass channel on easily erodible bed materials at 6 feet per second. And those guidelines indicated the permissible velocity could be increased 25% to 7.5 feet per second in the event the return periods of the flows are more than 100 years. Sometimes this is what happens when the statistics people get a hold of things and start changing things, not regard to physics, but respect to probability. Design report was also indicated that channel entrance velocity exceeds 6 feet per second for about 8 hours and 7.5 feet per second for 4 hours. Okay, in my opinion, this exercise should have ended right there. You had velocities higher than what even one guideline permitted, even with saying that it might be permissible at high values like 7.5 feet per second if it occurred less frequent than 1 every 100 years. Okay, the velocities along the outlet channel were not discussed in the design report. That's a part of the channel more than 100 feet down from the structure on the 1.8% slope, where those velocities, if you look at that carefully, could have been on the order of 14.5 feet per second. So for the May 14th event, not the PMF, breaching occurred at 1485.6. The horizontal critical reaches, the velocity reached about 8.5 feet per second. On the 1.8% incline channel, it could have reached 9 or 10 feet per second with reasonable calculations from typical Manning coefficients that probably existed. So, in the design report, they give the grain size distributions of the foundation materials. If you looked at a unified soil classification system, those would give you an SP or SM or an SM, SP, but certainly nothing like rock. You're talking about materials that cannot withstand a very high velocity, maybe not even more than 2.5 or 3, or certainly not more than 4 feet per second. Mike Duncan is here, I see, and so our field inspection, we thought they were silty sands with some gravel pieces in the upper 25 feet. Certainly not the kind of materials you would put a fuse plug on and say that the base isn't going to be going lower than the 1481. That's all I want to say about that. It's a case where the fuse plug, as far as activating, performed exactly like it was supposed to. When the water level got up to the pilot channels and a little bit higher, it failed. What didn't perform is it didn't stop at the base. It kept going on through the base and emptied the whole darn lake, not just the upper 5 feet like we're supposed to. If you employ a fuse plug, you really have to be right on the erosion. If there's any doubts in your own mind, you don't use them. Don't use the fuse plug if you're not that sure about the base. I got one more case history I want to include, and it's a Taum Sauk failure where the pump storage upper reservoir was on top of a hill. They were about 850 feet higher than the lower reservoir. Then there was a failure of the whole thing coming down the side of the mountain. And this was in December of 2005. Let me jump to that. I was going to show you what we got now at Silver Lake, but it's very good. You see, one of the reasons why they went to the fuse plug, they really didn't think they have a nice rock foundation for a regular type of spillway. Okay, this just shows a new fuse plug, a new conventional concrete spillway built right within the site of the existing low-level spillway, the low-level outlet. It was known that that was a structure in rock. It's also known that the old spillway was on rock. And if you just walked along the shoreline over here without taking a boring, the board could see that we had rock to build a new spillway on. And so could the new engineer determine that. Okay, so we got a project now where the embankment levels have been increased. We got a new spillway which will pass the outflows of the PMF. It's going to pass it safely because we're not relying on the road. It's on a rock foundation, and there's no reason why it shouldn't work well. So the old exercise was one where the improvement made the project worse. The improvements for the PMF resulted in a breach of the whole damn reservoir for 4.5 inches of rain. The next failure is the upper breach of the Taum Sauk spillway. The Taum Sauk Dam. The independent consulting panel consists of Joe Ehas, that's in the audience, myself and Kermit Paul, a mechanical electrical engineer, because a key in the failure for the Taum Sauk reservoir was the measuring system for the water levels. Okay, now when you look at Taum Sauk before the failure, I think you have to come to the conclusion that reservoir is quite full. Okay, now, even I can tell that. Now, there's several things about this. This is a concrete face rock-fill dam built in 1962, put into service in 1963. It's dumped rock fill. And then in the dumped rock fill, the downstream slopes are 1 and 1.3 horizontal. And it's the same on the upstream side. And on top of that embankment is a 10-foot high wall, cantilever wall, and the water level was stored anywhere between 6 and 8 feet up in that wall. Not due to a flood, because we got something worse than the PMF here. We got a reservoir and controlled by people. And that also is not a joke. It's real. And that can be worse than the PMF, naturally. Okay, so that's why it looks full, because under ordinary conditions, it got to be towards the end where due to the settlement of the rockfill, the settlement of the top of the wall, the reservoir level every day went to within 1 feet of the lowest point on the top of that wall, which is not, in anybody's measure, an acceptable risk. It's not an acceptable freeboard. Okay, here's where the breach occurred. Okay, now keep in mind that this is some 850 feet higher than the lower reservoir in the lower topography. And this was what it looked like in the breach area the morning after the failure. I got a call from FERC on the morning of the failure. It failed at 5:15 in the morning and I think it was on the 15th of December. And drove down there and inspected this zone literally hours after it was formed. Okay, if you look at what happened, you'll see this is where it went. It wiped out all the trees and everything way down and around this corner, and eventually got to the lower reservoir right here. The dam, as I mentioned to you, was a concrete face rock-fill dam, and the following things should be noticed. It had a 10-foot cantilever wall on the top, and water initially, the top of the embankment was 1589, the top of the concrete wall was 1599, and the reservoir elevation every day was to be 1587. I'm sorry, 1597, within two feet of the top of the wall, not accounting for settlement of the rockfill that was going to occur later. The other thing about this design is that you're in an area that was not glaciated, and so you got a certain thickness of saprolite, weathered bedrock, and on top of the saprolite you've got residual soils. And the jobs that I work on that involve concrete face rock-fill dams, the recent one was one 205 meters high or 650 feet high in Borneo, where we have deep residual soils. We excavate everything under the footprint down to unweathered rock. On that particular dime, it meant excavating 10 million cubic meters of material. Okay, here, only 70 feet downstream of the plinth of the dam was supposed to be excavated down to unweathered rock, and from there downward, everything was left in place, which means you got a very steep slopes. It's not like an embankment dam of soils, where you got an upstream slope at 2 on 2.5 to 1, and you got 1.75 to 1 on the downstream side. Here you got very steep slopes on both sides, and even if the rockfill can take it, sometimes the base can't take it, and you got to get rid of the weak zones or you're risking a failure. That's the kind of decision that you should make without trying to make a slope stability analysis. I'm sorry. It's better off to have the philosophy of removing that under the full footprint, period. You don't have to justify everything by a calculation, especially if it's a decision on the conservative side. Okay, this is just a picture which I don't want to talk about. The cantilever wall is 10 feet high. The only other thing that you can see, you see that it's a very slender wall for as high as it is. It's a foot thick. You'll see that later, over a significant number of panels, they changed the design. I think it was because they observed poor performance of the thin cantilevered wall and made it a little bit more substantial. I want you to see the failure occurred over here. And that's about between panels 88 and a little over 100. This is where it failed. The low point on the wall after the years that it was built was over here at panel 72. It had settled 2 feet there from the time that the project was built. There's another part, panel 95, in the middle of the section that failed, which is one of the next lowest ones. Okay, so when the reservoir level came up past a certain amount, those were two of the key locations where it overflowed. Where it's red, it overflowed and failed. Where it's blue are locations where it overflowed. And we got that many overflows taking place. It means you're just being too daring on the level that you're putting it up. You shouldn't have plans to put the water level up where you have such small freeboards. The performance of this dam, it was put into service in like July 1963. By the fall of 1963, there were some places where there was leakage. There's some places, one of the benefits of the pump storage is you can run it up and down every day. Okay, so you don't have water there all the time. When it's empty, you can see where there's damage on the inside. And there was significant damage that required a lot of work on the inside in the areas of panel 90 through 95, which ended up also being as part of the failure years later. If you compare the precedent to other rock-filled dams at the same time that were built, there's a key comparison. This is Taum Sauk. These are rock-fill dams built in the USA that were concrete face rock-fill dams. Taum Sauk was here. It's one of the last dumped ones that was built, and that was between 62 and 63. The solid points are dumped rockfill. The open points are compacted rockfill dams. Now, at the same time, there was a dam 230 feet high, Cabin Creek in Colorado, also pumped storage, that was built at the same time, so the state of the art is the same. It was compacted in 2-foot lifts rather than dumped. The slopes on the upstream side were 1 on 1.3, the same as Taum Sauk, but the slope on the downstream side was 1.75 to 1. This is Cabin Creek Dam. If you want to look, you should also look at precedents and not of other dam failures, but on the same problem, those that performed adequately. Okay, this one performed adequately. One of the reasons it performed adequately for a long time is that you'll see that the operating level was down here at 11,196. The crest of the embankment itself was 202, so you had a freeboard there of 6 feet. There was a parapet wall on top that was 3 feet, so you really had a freeboard, if you wanted to count the wall, of 9 feet compared to 1 or 2 feet at Taum Sauk. The way that it turns out, neither one of these projects had a spillway. Why? Because people assumed with people in control instead of the weather, that there's no problem. Well, it so happens that Cabin Creek also was overpumped. But Cabin Creek didn't fail. It didn't fail because, first of all, it didn't have water stored on a 10-foot high wall, so when it starts going over there, if you take the square root of 2GH, it impacts the embankment at about 21 or 22 feet per second. It's no small joke that you have that water stored 10 feet above the crest. Here, that wasn't the case. And this happens to be one done by Stone and Webster and Bill Swiger, okay? And they did the right things, and they experienced overpumping due to the level of controls in the water level measuring systems, and it survived. It survived because everything done was one more step conservative. And when you compare these two projects, it really is a comparison of the willingness of certain individuals as consultants, certain engineering companies that are doing design, and certain owners, and the risks that they're willing or not willing to take. If these two things were built at exactly the same time, the state of the art was the same. The end result wasn't the same. The Taum Sauk case, even though it has the weaknesses that I mentioned to you, it was put into service in 1963 with all these things that happened where it had to be fixed on the upstream side. And it happened to be that a lot of those fixes were right where it ended up failing. It did survive with the normal ups and downs, but there was not enough reserve capacity there to tolerate overtopping. So the root cause of the failure still is those causes that caused overtopping. Here is a settlement. Okay, it shows that the settlement was on the order of 2 feet at the lowest point, which is panel number 72. The average of all these is about a settlement of about 1.6 feet. Okay, here's the other thing that happened. Over the years, you can see from early on, you got measured flows on the order of 20, 30 cubic feet per second. Every once in a while, some peak goes up. But in this area here, which is 1999, 1998, the leakage started going up significantly, where we got a lot of leakages around 60 cubic feet per second, every once in a while up around 100 cubic feet per second. And during that time, it was decided the leakage was too much, there was too much risk, and there was a geomembrane put around the whole thing. I think a lot of expense to the power company, and rightly so. The leakage was reduced to 5 cubic feet per second. Okay, that was the plus. The minus was all the years previous to 2004, they had a water level measuring system where it used to be a float and a skate thing, which is a simple thing. That float worked from 1963 to about 2000. And it never overtopped. Okay, from 2000 to 2003, they took the float out because that was old-fashioned, I guess. They put pressure transducers on the same structure which was bolted to the concrete face. Those pressure transducers, where you know the position head, you add the pressure head so you know what the level is, that worked from 2000 to when this thing was fixed in 2004. Okay, when they fixed this thing and got the flows down to 5 cubic feet per second, that dam was probably more stable than it's ever been in its life. The flows were the smallest. Piezometric levels, if there were any on the downstream side, had to be lower than any time in the past. But what happened was they tore out the old structure on which the previous pressure gauges were installed. They replaced it with pressure gauges that were mounted on something that wasn't fastened to the concrete face. Why? Because they thought it was virtuous not to poke holes in the new sacrosanct liner. Okay, so they built a structure there, and I'll show you this structure. This structure is supported by cables on some base plates. And here you see in the construction that was done, this was not fastened to the concrete face. And you'll see some sloppy work there where this thing was supposed to be bolted to the cable to support it. The lock washer is left off. This thing is totally loose. And this thing got to be free to move. There's how much it moved. Okay, so what happened was the position head was assumed to be constant, but the position head was changing. They were measuring the pressure head, and they were getting inaccurate water level measurements by 2 to 3 feet. And what happens is it can't go lower, but it can go higher. So the position head can be higher, and so you're always going to be predicting or measuring water levels that are on the low side of the actual. So the actual water level is higher than what is the measurements, so-called, are indicating. Okay, how come it moves that much? Okay, I'll show you something else. You see, this is where the measuring system is. You see where it is? What's that? That's the shaft that goes down 850 feet to the powerhouse. Okay, when the water level is either going down there when it's generating or coming up, you got a vortex. And this is how come you get the bias movements of that thing when it's not fastened to the face. Okay, so one of the root causes of the failure is the fact that this water level measuring system isn't measuring the water level. And it's measuring it on the unconservative side. In addition to the water level measurements, which now we know are one of the root causes because they weren't measuring the right water level, there's supposed to be some Warwick probes, some electronic probes set on the wall, so when the water level came and they shorted out, they stopped the pumps. Okay? Now, that's a darn good system. The water level doesn't make it. It's a last resort to control the water level, or at least to shut off the pumps. Okay, now these probes were installed initially at elevation 1596.2, 1596 for the high probe and the high probe. And the way it was, the high probes were the only ones that really would, when they shorted out, would shut off the pumps. This here was to give them a warning or something, but the key to look at. Okay, now if those were there, that would have solved the problem and it would not have overtopped. However, when they went into the field after the failure, they found that the high probe was up here, not where it was installed. Okay, so it was up here at 1597.7, okay? Now, panel number 72 that I told you was the lowest one, the top of that panel is 1597. So that panel, which is shown here, 1597, could be overtopped. And panel number 95, which we know now is in the center of the real breach, where I showed the red area for the panels, That was at 1597.4. Okay, the highs were up here, 1597.7, where the water level could come up here. You could get overtopping, and those high probes weren't touched, and they didn't turn off the pumps. Why? Because somebody moved them. Now, in our activities on this, Joe can attest to that, we interviewed a lot of people who were associated with this. We never could find out when these things were moved and who moved them. But they were there. Okay, so the backup system didn't work, and the original system was no good. It wasn't near as good as what was used between 1963 and 2003. So this isn't the last two case histories I've showed you. The improvements that were made to the project that the power companies paid for were the reasons why they failed. Now, this, I'm not trying to make fun of our profession. I'm just stating some facts on it. All I did is go back for the only jobs, not because they're big and I've got all kinds of those, but those that resulted in an actual breach where I found out what was going on with others because we participated in a panel investigation. And the last two are kind of depressing. And there are things to learn from that, but they're things that you shouldn't have to learn. I have to say that. Well, that's all I wanted to present. I shortened it up so you folks can get to eat. Okay. Yeah.